Hello everyone, H. Reddy, working as the assistant professor in Thyristor Engineering College. Welcome to my channel. My channel name is Accelerate Your Research. Okay. In this video, I will explain power quality and pack subject. Okay, this is my channel, Accelerate Your Research. In channel, have playlists. Click here, view full playlist. This total 8 videos. In these 8 videos related to power quality and pack subject. First chapter and second chapter, unit 1 and unit 2. Now I will explain first syllabus in unit 3. This is the R18 syllabus, JNTU H, power quality and pack subject. In my previous videos related to unit 1, power quality problems in distribution system and transmission lines and series and center reactive power compensation. Okay, this total first unit and second unit. Total these 8 videos. Now, today I will start unit 3. Unit 3 is a shunt compensators. In the shunt compensators, objectives of shunt compensation, methods of controllable VAR generation, static VAR compensator, its characteristics, and TCR, Thyristor-controlled reactor, Thyristor switched capacitor, next fixed capacitor, TCR configurations, STATCA, basic operating principle and control approaches. This total unit 3, shunt compensation. I will start my presentation with PPT. Okay, these are the content. Unit 3, static shunt compensator. Objectives of shunt compensation. The main objectives of shunt compensator is improving power quality and compensation of reactive power. These two main objectives of this shunt compensation. Next, methods of controllable VAR generation, static VAR compensator, its characteristics, Thyristor-controlled reactor, Thyristor switched capacitor, and FC-TCR configurations. This video I will cover static VAR compensator and TCR. TCR means Thyristor-controlled reactor. This is the basic definition of SVC. By definition, capacitors generate and reactors. Reactors means inductors absorb reactive power when connected to the AC supply. This is the static shunt compensator or SVC definition. This is the SVC structure, a static VAR compensator. Static VAR compensator means the shortcut form SVC. Okay, this is the SVC. In this SVC, subtopics are Thyristor-controlled reactor, next Thyristor switched reactors, harmonic filters, and mechanically switched capacitors and mechanically switched reactors. This total subtopics. Subtopic means here in this TCR, TSC, FC-TCR. This total subtopics in SVC, static VAR compensator. Okay. In this static VAR compensator, mainly used for two purposes here. SVCs are used in two main situations. One is the connected to power system to regulate the transmission line voltage. One is the to regulate the transmission line voltage purpose. Second one is the connected to near large industrial loads to improve power quality. This SVC is used for mainly this industrial purpose. One is the power quality improvement in industrial. Second one is the regulating transmission line voltage. These two purposes, this SVC used. Next year, a static VAR compensator is a set of electrical devices for providing fast acting reactive power on high voltage electricity transmission line network. Mainly this SVC used for improving power quality and compensating reactive power. Okay. In light load hours, this TCR absorbing reactive power. In peak load hours, the capacitor banks will generating reactive power. Okay, this SVC observing and it generating reactive power. During light load hours, the reactive power observed will TCR. During peak load hours, the capacitor banks will generating reactive power. Next year, the SVC is automated impedance matching device designed to bring the system closer to unity power factor. This SVC used for maintaining unity power factor. That is one more reason. SVCs. This is the total structure of SVC. In this one by one, I will explain. This is mechanically switched reactor. In this mechanically switched reactor, inductor series with one switch. Okay, mechanical switch. Next, this one is the Thyristor-controlled reactor. In this Thyristor-controlled reactor, have here two thyristors. This is the first one, second one, and here two thyristors connected anti-parallel. Okay, this is the thyristor 1 and this is thyristor 2. This name is the Thyristor-controlled reactor. Next, this is shortcut form TCR. This is the TSC, thyristor switched capacitor. Okay, here this capacitor, thyristor switched capacitor. In this thyristor switched capacitors also have two thyristors. These two thyristors connected in anti-parallel. One thyristor connected in positive half cycle. Second thyristor connected to the controlling negative half cycle. This is the harmonic filter. In this harmonic filter, this is the capacitor C LC filter. This is the C filter, only capacitors. This is inductor. This is the thyristor switched capacitor. This capacitor. This is the just line distribution line. This is the grid connection. This is the grid. This is the step down transformer. This step down transformer stepping down high voltage to low voltage. Next, this is the mechanically switched capacitor. This is the mechanically switched capacitor. In this capacitor have one switch. This total, this inductor, this four of the distribution lines. Okay, this is the capacitor, the reactor here. This is the capacitor. This is also capacitor here. This one is the mechanical switch. Okay, this is the SVC, static Var compensator. Next, this is Thyristor-controlled reactor. Thyristor-controlled reactor. This is circuit diagram. This Thyristor-controlled reactor have two switches S1. This is the switch 1 and switch 2. Two switches connected in anti-parallel. One inductor connected with the series. This is the distribution line, transmission line. This transmission line, this inductor, this Thyristor-controlled reactor connected sent or parallel with across the load. Okay, this Thyristor-controlled reactor mainly used to function. The Thyristor-controlled TCR function is it observing reactive power when light load hours. When light load hours, this Thyristor-controlled reactor observing reactive power. In this circuit, it consists of a fixed, usually air-cooled reactor of inductance L and bidirectional thyristors value. Here, this fixed, usually air-cooled reactor means this one. This inductor is air-cooled reactor, and this bidirectional thyristors means these two thyristors are bidirectional thyristors, like AC voltage controller. One thyristor controlling positive half cycle, second thyristor controlling it negative half cycle. These two thyristors. Next point, this is the Thyristor-controlled reactor can be used for limiting voltage rise on light loaded transmission line. This is the one more reason for using this TCR. Thyristor-controlled reactors can be used limiting voltage rise on light load transmission lines. Next, the ratings of voltage and current. Currently available large thyristors can block up to 4,000 to 9,000 volts each thyristor. This thyristor blocking voltage range 4,000 to 9,000 now available in market. Next, current rating of thyristor is 3,000 amperes to 6,000. This third point related to capacity of voltage capacity and current capacity of thyristors. 4,000 volts to 9,000 volts, and the current limiting is 3,000 to 6,000 amperes. Next, in practical value, many thyristors typically use 10 to 20 are connected in series to meet the required blocking voltage levels at given power rating. In practical applications, in megavolt ampere or kilovolt transmission, 220 kV, 220 kV or 440, 400 kV transmission, 33 kV, 66 kV, 132 kV. Many transmission lines have capacity is very high. Okay, for this purpose, one thyristor is not sufficient for blocking voltage. That's why in practical application, 10 to 20. For example, one thyristor value is 4,000 volts. If 3 thyristors connected in series, the capacity of blocking voltage is 12,000 volts. Okay, in practical, 10 to 20 thyristors connected in series for blocking voltage levels at given power rating. Thyristor value can be brought into conduction by simultaneous applications of gating pulses. All thyristors the same polarity. The thyristor's value can be conduction by the simultaneous applications. Gate pulses are all thyristors same polarity. Next, this is the TCR. TCR means Thyristor-controlled reactor, mainly used for the main operation. It observing reactive power when light load hours. Okay, these are the characteristics of Thyristor-controlled reactor. Okay, this is the V is the supply voltage. Supply voltage means voltage across this point, these 2 points, starting point, and or voltage across the thyristor controlled reactor. This is the supply voltage V. This is the IL. So IL means current in inductor or reactor when alpha is equal to 0, firing angle 0. Okay. The phase difference between voltage and current is 90 degrees. The operating range of thyristor firing angle alpha 90 to 180 degrees. These two thyristors not operated like ACVC. ACVC means alternating voltage controller. Okay, this thyristors start from 90 degrees to operating from 90 to 180 degrees. Here supply voltage starts here. Okay, after 90 degrees, the current is starting here. In this inductor current, it increasing time and decreasing times both are same. Here volt second balancing formula here applicable means here 0 to here. For example, 90 to 180 degrees, the current increasing. Again 180 to 270 linearly current decreasing. Here also, here IL inductor current with some delay angle alpha. Here alpha is the delay angle. This is the sigma is the conduction angle. In this delay angle, current start from here to here increasing, here to here decreasing. Okay. In alpha is equal to 0 and alpha is equal to some angle. Okay. The waveform magnitude here decreasing. When we are applying alpha is equal to some angle, the magnitude of current decreasing. This is the total positive off cycle. This is the alpha is the firing angle. The sigma is the conduction angle. Next, this is the negative off cycle controlling thyristor. This is the alpha. Alpha is the firing angle. Next here sigma is the conduction angle. This is the negative. This is the thyristor T1. This waveforms controlling thyristor T2. Here T2 also. This is the voltage across the TCR. This is current in inductor. Alpha is equal to 0. Here IL of alpha. Alpha means firing angle. Here we applied some firing angle. This is the this waveform reference NPTEL. They copied this image from NPTEL PPT. Firing angle alpha is equal to 0, measured from peak of source voltage. This is the input waveform. This is the input waveform. This is the current waveform with alpha, firing angle alpha is equal 0. Okay, this current waveform start from 90 degrees, conducted to 180 degrees. Okay, cycle repeating like this. The increasing time and the decreasing time both same in TCR. This waveform alpha is equal to 30. Next, here this is the waveform. Firing angle alpha is equal to 30 degrees. Okay, 90 plus 30, 120 degrees. Here, the waveform current waveform start from here to this period is total conduction period. This is the alpha value, firing angle. Okay, when increasing firing angle, the magnitude of current is decreasing. Okay, observing this waveform, comparing to previous waveform. In this waveform, the magnitude of current decreasing when firing angle alpha is equal to 30. Again, this is the firing angle alpha is equal to 45 degrees. The magnitude of current decreasing when we are observing this waveform. When increasing firing angle, the magnitude of current is decreasing. The conduction period also decreasing. Okay, this is the operating waveforms. This is the supply voltage. This is inductor current IL of alpha. Okay, this is supply voltage. It maintains constant. Here alpha is equal to 0. When alpha is equal to 0, the current is IL of alpha is maximum. When increasing alpha firing angle, the magnitude of current decreasing. When alpha 2 greater than alpha 1, when increasing alpha 2 firing angle, when increasing firing angle, the magnitude of current again decreasing. Okay, observe in this waveform clearly. Alpha 4 greater than alpha 3 greater than alpha 2, alpha 2 greater than alpha 1, like this. Then increasing firing angle, the current of the waveform current, the magnitude of the current is decreasing. Okay. One more important point: the magnitude of reactive power is directly proportional to the inductor current in Thyristor-controlled reactor. Okay. One important point: the magnitude of reactive power is directly proportional to the inductor current flowing through the inductor current. Okay, this is the total related to TCR, Thyristor-controlled reactor, and SVC. Okay, thank you for watching this video.